Whose screen is that up there?
Well, that's,
His.
well, that's mine, but I set this over to podium input, okay? So,
See, so we've got this picture here that nobody else can see. This,
Yeah.
nobody else is seeing this picture.
okay, just you and me, because that's that camera right
Right.
there. Ah,
But you're hearing audio, and if someone in the audience says something, you probably hear them too.
Yeah, we're getting audio, just no video.
uh-huh.
And I inadvertently started the stream.
That's fine. We'll.
All right, well, let me, for the benefit of everybody who drove out here, perhaps I should take it from the top while we work on our technical issues.
Yes, I'll just keep
All right.
figuring it out.
You need anything else out of that packet, Adrian?
Not sure there's anything else I'll be able to use.
All right, gang, remember we can hear everything you're saying.
Yeah.
Okay, taking it from the top, thank you very much for joining us tonight. We apologize for the technical difficulties, but it's part of our ongoing effort to bring a hybrid experience to those who are not able to join us in person. For those of you who've not attended a meeting before, I am Diane Hall, the current president of the club, and this is our third in-person meeting since March of 2020. Do we have any new members in the audience tonight, or newcomers, guests, people who've not come before? Hello, welcome. What's your name?
Catherine.
Excellent. What brings you here? Word of mouth. Fabulous. Well, thank you for coming. So, the board had a jam-packed meeting tonight. We've got a lot on our plate at this midpoint of the year. We've also got some fun things for you. Up here at the front of the room, we have 3 calendars that were never picked up by their intended recipient at the beginning of the year. Of course, it's July. These calendars will be available for the discounted price of $5 a piece, and you get to enjoy all of our wonderful artwork. So if anybody would like a calendar, they're right up front. Adrian, our treasurer, is right up front. Slip Adrian a 5 or give him a card, and you'll be able to, go home with a calendar. Another thing we have is some wonderful books that Mark Kedzier has brought in, and I believe these are all free, Mark?
Yes.
Donations for the public good. So if you would like to go home with some lovely books, check it out. We have a picnic coming up on the 27th of August. It is our normal picnic format at Wolcott Mill. The club will be providing burgers, dogs, vegetarian burgers and dogs pop, and also ice and condiments, and we'll be doing the work of actually grilling. All you are required to do is bring a dish to pass. We'll be eating, of course, in the open air under the pavilion. We're going to be having an informal swap meet and hopefully observing to follow. So we expect that that'll be a good time. The only variable left is the weather. We also have discussion group is back up and running in person. I understand many members do have reservations about that, but we are trying it for the very first time. Laura Wade, our hostess extraordinaire, is welcoming people into her house on Wednesday, the 26th of this month. Is it? Yeah, I thought it was. We've got the date in the WASP. You must be vaccinated. So barbecue pork roast will be provided, 6:30. So check out the latest issue of the WASP for the address. And thank you very much, Laura. Again, vaccinations required. Very good. All right, a couple other things from the top before we switch into the rest of the officers' reports. We're discussing the viability of an in-person banquet this year. We will be sending out a survey. Please take the survey. It'll be very simple. Indicate whether or not you would be willing and able to attend an in-person banquet, and if no, why not? If it's you're out of town, cool. If it's I don't want to get COVID, also cool. Neither do we. But you know, if it is viable to do a banquet, we would like to have a get together at the end of the year. Yes. Yes, Laura. Thursday. Thank you, Laura. In big news, Don Glazer, our liaison here at Cranbrook, is on the verge of retiring. He's worked with the Ford Club, he's worked with us, he's done extraordinary things. So if you see him tonight and he is back there in the control room, do express your thanks, because he's done, he's helped keep things afloat for us. And I think everything else can be covered under the officer's report, so I will yield the floor to Bob.
Hi there, I'm Bob Tremblay, your first vice president. Our speaker tonight is got his tech working, and I'm looking at his bio. Holy mackerel! It's going to be an interesting read when I do this. Our meeting on the Macomb meeting next week, or our next Macomb meeting, we're going to be doing a panel discussion about our memories of Apollo. And I got this idea from our banquet a couple years ago when the speaker asked the audience, you know, how many of you saw Sputnik? And half the audience raised their hands, and I'm like, I wasn't even born yet. And so I would like to have some input from people that saw that. And, you know, I was a child during the Apollo era, so that should be an interesting panel. It's going to be fairly informal. I was in contact today with an instructor from the University of Michigan, and she gave me contact information for one of her grad students, and she wants to do a presentation on exoplanets. For the Vatican Observatory, they're putting together next summer their summer school program, and I sent out a blast to all the previous summer school students, and one of them contacted me back, wants to be an instructor there, and he is also working on exoplanets, and he's working on big data machine learning in astronomy and stuff, so we might have a presentation on that. So that's it for first VP.
All right, thank you, Bob. Riyad Mahdi, second vice president.
Thank you, Diane. Hello, everyone. Our last Stargate open house was June 25th. We opened the observatory at 7:25. It was cloudy, unfortunately, as it has been for most of this year so far in our open houses. I'm hoping we will start to have some clear weather coming up in the next open house. We had about 50 people that attended, including 4 members, and there were some scouts out there with their leaders. I gave a presentation to the scouts about the observatory and answered some of their questions on astronomy. Bob Berta was there as well, and Jeff McLeod, and they also helped to answer people's questions on astronomy and did some observing. We had a 6-inch reflector out there, Dobsonian, as well as the 10-inch Dob from Stargate. We did a little bit of observing of some double stars, the brighter ones that came through the thick haze. Most people left around a little after 11, and we closed the observatory about 11:22 p.m. Next open house is July 23rd, so hopefully we'll see everybody out there. Also, just one quick note, we'll try to clean the 22-inch Dob optics during the picnic, the upcoming picnic. So we'll need to have, maybe if we could have some of the members of the observatory committee and some other people out there too, some of the members that would help us out. The stuff is a little heavy and need some help with it. That could be something that maybe you can participate in and we can work on. That's all I have right now. Thank you.
Thank you, Riyadh. All right, on to Mark Kedzier, the secretary. Come on up, Mark. Yes.
Hello, everyone. The minutes of the June meeting are in the WASP. And speaking of the WASP, I really enjoyed the last issue. It really is a top-notch publication that we do. A lot of good names in there and everything. And Astrophotos, really proud to be a member of this club. That's my report.
Thank you, Mark, and thank you for bringing in the lovely books. Hopefully we leave here with no books tonight. Adrian, back in the control room, are you able to give your treasurer's report? I'm not sure if that's a thumb or not. Adrian, do you copy? All right, Kevin, you're on.
There's two events that are coming up. One is on August 11th, and it's at Cranbrook. And they have an exhibit. What's the exhibit? Treasure. And so it's and that I think is a members only night and so we're looking for anybody who has a telescope to come out to support it. It's the Perseids meteor shower, but anybody with telescopes or anybody can come out to volunteer. Just as a reminder, the reason we have this room is because we support the events at Cranbrook. So we need to support it as a club. So anything you can do would help. And then the astronomy at the beach is the 16th and 17th. We're looking for volunteers. Again, anybody who has a telescope who wants to come, but we also need volunteers. I'm going to send two emails out. I'll send one out in the next day or so, just to the people who typically volunteer, and then I'll put together a roster of them for those two events. And then I'll send something out to the rest of the group also, just to see if we can get any more volunteers for that. Okay, and Diane had one thing to add about the astronomy at the beach.
Thank you, Kevin. So we customarily have our big dub at Astronomy at the Beach. It is a very long drive from Ray Township. We had a flat tire at least once in recent years. Jeff McLeod, who's currently been the telescope hauler and running the telescope, is not able to do it. He has a scheduling conflict. He unfortunately cannot get around. So he asked if I could appeal to those who are able to transport and assemble and run the Big Daub, which is a pretty small subset of the club, to bring it to Island Lake, if at all possible. If not, yeah, that's a big haul. I mean, that's going to be 2 hours there and back, and plus running the telescope all night long. If you can and you're up for it, please contact the board. If that is not something you can do, we understand. It's not easy. But it is nice to be able to offer the public our 22-inch telescope someplace other than Stargate, which is where it lives. All right, and with that, Dale Teamy at Publications.
Okay, I'd like to point out that the WASP is online for this month. We managed to get it on, and point out that for 2 months running, Adrian Bradley has made the front cover, mainly due to the fact that he won an award with the Royal Astronomical Society of Canada. So I thought that was worth mentioning.
Indeed.
And that's what I got.
Award-winning photographer Adrian Bradley. Can you hear us back there, Adrian? He changed your status, but I don't think he can actually, I don't think he's broadcasting. Bummer. Anyway, we've got Captain Marty front and center. Marty, what's the solar subgroup report for the month? Marty? Well, I would, but my telescope, my computer can't go up there.
sun's actually getting Mars and going with activity slow, but the I definitely home the sun right now, so quite active every activity, having lots of activity.
Captain Marty, the solar subgroup says the sun is active, ladies and gents. So check it out. Riyadh, any update on the double star group?
Yeah, every time we meet at the observatory, whenever we have a chance, I usually have my observing list with me. So the same thing is for the coming up observing session for next month on the 27th. So I'll have the list with me again, and we can go through the through our favorite doubles and some very difficult ones as well, depending on the weather.
Sounds like fun. All right. Discussion group captain Jeff McLeod says we are open for business. If you would like to host one of the monthly discussion groups at your house, your place of work, your backyard, your local park, what have you, contact Jeff McLeod and he will be happy to get you in the rotation. Alcor, Adrian Bradley, has sent in the dues for this month's, well, this part of the year. So everybody's Astronomical League subscriptions is up to date. And we have online, we've got one, and here in Cranbrook, we've got the other captains of the astrophotography group. Bill, Doug, you got anything for us? Nothing from Bill right yet. How about you, Doug? I know the Northern Cross was up and running recently.
Yeah, I hope people have been getting out on all this clear weather we've had over the last couple of weeks. I know it's full moon this week, but new moon week was excellent. We had several nights that were clear, and I did a bunch of imaging of various objects. Plus, been hitting that comet Pan-STARRS this last month, and I'll have a report probably in the next newsletter for that.
Excellent. Well, that segues nicely into our observing reports. Online participants, throw up your hand since all I can see are little gray boxes. You'll need to actually hit the raise hand button for me to call on you. Otherwise, do we have any?
David is raising his hand.
Excellent. Take it away,
Can
David.
you hear me?
I can hear you.
Oh, wonderful. Okay, I'd like to say that I concur that the sun has been extremely active this week. I mean, just today I counted 53 sunspots. Yesterday there was a very large filament and multiple flares in hydrogen alpha. Just a beautiful, beautiful sun. This is a really strong cycle. And for my poetry tonight, I have from Milton, Paradise Lost. And there are two little quotes. And one of them he says, through optic glass, the Tuscan artist views an evening from the top of Fiesole, or in Valdarno to descry new lands, rivers, or mountains in her spotty globe. And then later, by name, he says, and when by night the glass of Galileo, less assured, observe imagined lands and regions on the moon, or pilot from amidst the Cyclades de los Hacemos first appearing kens, a cloudy spot. I understand that the only person, the only human being referred to by name in the entire epic of Paradise Lost is this one, is Galileo. Thank you, and back to you. Thanks for letting me do my little quotation. Thank you.
That is one of my favorite parts of that poem. So thank you. Any observing reports from the audience here at Cranbrook? We have had a slew of clear nights. Kevin's got his hand up.
Just quick, I was up there on the heavens. Sunday and Saturday, weird that it was closest to, it was a little bright at night. Sorry. Where? right, if you're up in Mackinac City, just to the west of Mackinac, so it's right at the top of the, we were staying at the top, we were, beautiful night to see the Milky Way, they was gonna go there and just get there, a lot of people, the parking is tight, really great.
Excellent. Thank you, Kevin. Jonathan and I were observing this past weekend from our area near Neguagon dark sky site, which we just took out our 10-inch and spent a while scanning through around Ursa Major, a bit in the Milky Way, basically just hitting a bunch of Messier objects and having fun. Hadn't done anything like that in a while, so. Any other observing reports from the in-person audience? Yes, come on up. Beautiful. Yes, Alberio, one of my favorite stars. Mercury's hard. Mercury was not at its best. Aldebaran, maybe, yeah, or Capella. Probably Capella. Capella looks awfully orange when it's right at the horizon. Nice. The coat hanger is a really sweet little cluster. Awesome. Any other observing reports? Anybody else from the virtual audience? All right, well, it's high summer. It's starting to get dark again at night, so we have slightly longer to get out there and see things. It is 8 o'clock. Bob, if you are ready, I will happily yield the floor to you for the short presentation.
Alrighty. Let's get this shared. I have got way too many windows open. Hold on a second. All right, you see a slideshow?
Yes.
Okay. So, hi there, I'm your first vice president. I'm Bob Tremblay. I am a volunteer NASA JPL Solar System ambassador, and I work for the Vatican Observatory Foundation. So I'm doing a recap. Last month, I did a overview of the decadal survey, and this is once a decade. NASA asks the National Research Council, so what should we do for the next 10 years? And these guys, they prioritize what we're gonna go after, the observations, and the missions required to make those observations. So it's a 10-year plan, and there are different ones. I'm covering the planetary science one. There's astronomy, astrophysics, and earth science, and I can provide a link for that. I actually like to have somebody else do a presentation on the astronomy and astrophysics ones. That'd be pretty interesting. So before we had the decadal survey, we had this thing. We had a plan, and there were a lot of things that were proposed, and the green ones were the ones that happened, the red ones didn't, and there were some that were proposed over and over and over again, and never happened, never happened, never happened. So again, the same thing here. There were things, mission to Uranus, and every one of these things, nope, didn't happen. Well, when the latest decadal survey came out for planetary science, the biggest well, they're including planetary defense, which is a really, really cool thing. But the flagship missions, the biggest one is the Uranus Orbiter and Probe and the Enceladus Orbilander, which I was telling my after school astronomy club students that for 2 decades I was just like, Uranus? No, no, it didn't happen. Well, it happened this one. And the choice, why they chose Uranus over Neptune, there was a lot of different reasons. They're both compelling objects. We have a lot to learn from them. They both have moons that would be very interesting to observe. But the reason Uranus was favored was because essentially we can get there on a current launch vehicle and no gravity assist required. Neptune Odyssey, we would our current launch vehicle wouldn't be good. We'd have to probably modify a fairing, uncertainty in power requirements, so it just wasn't viable. So Uranus it was. So it is the Uranus Orbiter and Probe. It's the highest priority large mission. Now this is a artwork I created in 2018 when I was posting. Boy, it would be nice to have a Uranus orbiter. So I'm very happy this happened. So I kind of modeled this after a Voyager. But the Uranus orbiter is a flagship mission, a lot like Cassini at Saturn. So it's going to be there for a while, doing a lot of different things. That's what it's going to look like. It's not sexy looking, but it's pretty cool. It's got like Cassini, it's got the magnetometer, it's a ton of different cameras, IR, spectrometer, and stuff like that. And I saw this. I said ultra stable oscillator. I said, what the heck is that? So I went and looked that up. That's what an ultra stable oscillator is. And this thing is going to be going on the JUICE mission. So when I looked at this, the specs, what the total ionizing dose was a spec I have never seen on a piece of equipment before. So yikes. So this thing is also, it's got a Mastrix spectrometer. I didn't create this slide, so there's your ultra-stable oscillator again, and hydrogen sensors and stuff. The blue thing that you see on the side of it, that is the probe that's going to go in the atmosphere. There's all the instruments, and again, it fits in a 5-meter fairing. Now it has, you'll notice here at the upper left, it's got 3 radioisotope thermoelectric generators. Now, as I recall, a couple years ago, there was a problem with plutonium production and lack thereof. Well, they're being reproduced, and I was amazed when I found this out that they can only produce like 1.5 kilograms per year. That's like not much. So yikes. There's the atmospheric descent probe. It has a lot of batteries and antennas and stuff. It's going to be there's atmospheric descent profile. It's got a drogue chute, larger chute, and it's going to drop down into Uranus's atmosphere and eventually get crushed. Now this is a whole lot like the Galileo mission from 1995 that did the same thing. It dropped a probe into Jupiter, and I'm all in favor of this. So again, it'll fit under a 5-meter fairing. It's gonna be launched by a Falcon Heavy, which we have now. There are launch windows throughout the 2030s. So and this is with and without a Jupiter flyby. So we've got lots of different opportunities to get this thing out there, which is a good thing. So it's going to orbit Uranus in a polar orbit. Now, okay, Uranus is flipped on its side, so yeah, there you go. But it's going to be studying Uranus's atmosphere and looking at its moons for subsurface oceans like Cassini found around Saturn. So it's going to be looking at the interior and origin of Uranus. Yeah, and what is it? Why is it? How did it form? How did it get there? It's going to be looking at its really bizarre magnetosphere. Uranus's magnetosphere is bizarre. It's not centered at all. It's offset. Why? We don't know. Well, this is why we want to go there. It's going to be looking at the rings and the satellites, the composition and the history again. Again, how did these things form? I mean, Uranus and Neptune are a lot different than Jupiter and Saturn. So I'm just so thrilled we're going out there. The other flagship mission is the Enceladus Orbilander. And that's a great word. It's the obligatory artwork. Gotta love it. So there's probe. It's going to land. Well, part of it is going to land on the surface of Enceladus. Orbit lander. That's a great word. It's a combination of orbiter and lander. I really hope to hear that some more. So this thing, flagship mission. This is crazy. Can detect life 500 times scarcer than Earth's ocean, and at surface levels 500,000 times scarcer. So it can find trace elements of life. Science objectives, it's gonna be looking for organic stuff, looking for amino acids, lipids. I can't even pronounce some of these things, and searching for those things. It's also going to be looking at the ocean constraints, the dynamics of it, and looking at the jets. So mission overview, science phase from 2050 to 2054. It'll be orbiting, and it'll also have a surface 2-year surface mission. Now I want to point out that by the time this thing gets there, my 2-year-old granddaughter here, who I slipped into this presentation, of course, she's going to be a middle-aged adult by the time this happens. So hope I'm around to see it, because I want to see it. It's going to be orbiting this thing right in the center here. It's going to be orbiting at either the L1 or L2 south polar halo orbit. And I said, what is that? So I went digging in the documentation. Now, before I show you this picture, most times when you think about orbiting a moon, that's what you're thinking, right? Nope. There you go. It's going to be orbiting the L2 halo points, a lot like the James Webb is orbiting the L2 point, the Earth Moon halo point. So that is a bizarre orbit, and you should see some of the documentation on this. It's just crazy. So the mission timeline, there's your mission timeline: 2050, 2055. If it's still alive and it's on the surface and its orbiter, I can guarantee you they're going to do an extended mission. That Cassini certainly did. So these are missions which were not prioritized in this round, and that's a little unfortunate. I got Neptune, Triton. Eventually, we'll get there, I hope. So I mentioned that there are other decadal surveys, and here they are. And if anybody's interested in putting together a presentation on the astrophysics, heliophysics, or Earth one, I'd be more than happy to have you present that. So we're going to be the decadal survey, and I'm going to be talking August 1st about the planetary defense portion of it, which planetary defense has been added into this one, and I am very happy about that. So with that, that's my presentation. Thank you very much. See you next month.
All right.
Yeah. This mic picks up.
Kill it, Adrian. Okay, thank you very much, Bob. Those are all great missions. Really happy that they're moving forward. At this point, we would like to take a 15-minute break so everybody here gets a chance to use the bathroom, grab something from the vending machine, and so we have time to work out what is going on with the audio here before our featured presenter, Tim Thompson, gives his talk on Mount Wilson. So see you all in 15 minutes, gang.
All right.
So some of the people in the auditorium,
I'm sorry, what?
are some of the people in the auditorium?
Yes, we have about 24 people here in
Yeah.
person.
Oh, okay. Yeah, I thought it was just an online meetup, but okay.
Yeah, we're doing hybrid meetings, hence all the problems, because hybrid meetings are challenging.
Mhm. Yeah, and there's preference as well, so, okay.
I remember when Cassini was on its end of mission and going to plow into the atmosphere. I was listening to National Public Radio, and there was somebody on who was with the mission from pen and paper, and they'd been with it through like 30 some odd years. And I was telling this to my mother-in-law, and she was saying, "Yeah, I remember watching those guys cry when that thing went into." I'm like, that was your entire career for some of these people, and that's going to be the same thing with these flagship missions.
Good point, Bob. Hey, Dale, Bob, those officers on remotely, and Tim, we are going to disconnect my computer and try to transfer everything to the PC in the back of the room, which should solve our broadcasting issues here. Bear with us while we take care of this. So if I disappear, we're working on it. Hope to see you within a couple of minutes. Think of it as like Apollo 13, but
Yeah.
with air.
And no duct tape.
And no duct tape. See you in a sec.
David, I wanted to dedicate my RASC photo to your support when you first saw some of my images. So thank you for your role in being able to do that. And it looks like you're on the cell phone, but thank you, David, for your role in helping me with that.
To the public saying just because you sign your driver's license, you're signing away your Fourth Amendment right to not be to have your identity seized just when you're engaged in a lawful activity. I've read the Georgia, stop and ID statute. If you have reasonable suspicion that I'm engaging in a crime,
Right.
yeah, you can identify.
All right, test. Are we
If I
transmitting?
don't, I'll be charged with failure to identify. But he said you're just suspicious, and I'm like, well, being suspicious is very subjective, sir. But again, I think
Chris, give a thumbs up if you can hear me.
especially one with the GBI, would think that just signing an ID is something that
Actor should be able to hear me back here. Yeah, I don't know. The audio, I don't know if the audio is working or not. You can hear me over there. That means the audio is working. So there, yeah, you all are able to hear me. Okay.
Dawn, test check, 1, 2.
I hear you.
Oh, good, I'm glad somebody does.
Hear you too.
So what do you do?
David, can you hear
These
me?
are for sale? No, they're free. They are? Yeah.
Yeah, I wanted to personally send you a note of thanks for your help, which has led to that award that I got from Nebraska. Oh man, I wish I could hear. Well, thank you. It sounds like we've turned down the volume in the auditorium, but thank you. Your support, the RASC has been very instrumental in just sort of igniting the passion to get out there underneath the stars, whatever our image.
Thank you, Adrian, but it's your pictures and your award. Congratulations.
I'm here, so I'm going to turn up your volume.
And I'm glad you're back, Adrian. I see you're.
Yeah, she had him on her machine.
Okay, now we can hear the echo. I think it's coming from that laptop though.
Okay.
But just know that I'll be forever gracious, and we will talk again soon, David. And I actually am doing a presentation this Saturday for the Montreal Center. Kareem has got me doing it.
I will be there.
Awesome.
Where is his voice going? Why can't we hear it?
It's just soft, but I heard him out of the speaker. So that may be a setting in the control room to turn up the volume from the system PC.
Let me see what I can.
Yeah. Here, I'm gonna go on mute, everyone.
Fucking with me. Damn it. Quitting it.
Bob, go ahead. Go ahead and say something, Bob.
So if I have my mic down. Hello, hello. Testing, testing, 1, 2, 3. Testing, testing.
Yeah, we can hear you. Okay, that's good. So we know how to turn the volume up upstairs. Okay.
Can you hear me or can you hear me? Test.
Folks up there in like virtual land, you hear me talking about that mic can sit up very good. That's our video, that's us. But it's happening. You know what, I'm gonna change that.
Test. Anybody hear me? Good. Thank you.
We can hear you, Ken. Very well.
Not hearing anything.
Nobody was saying
1,
anything.
2. 1, 2.
All right, everybody, we're closing in at 8:30.
One, two, 1, 2.
Bob, go ahead.
Testing, testing. Hello. Can you hear me?
Yes.
Yeah.
Okay.
Muted.
Okay, so we're ready to start? $8:30.
Go.
Okay. All right, our speaker tonight is Tim Thompson. He received his bachelor's in 1978 and master's at 1985 in physics from the California State University at Los Angeles. He joined JPL, the technical staff, in January 1981. I'm sorry. He joined JPL as a member of the Radio Astronomy Group and retired from JPL in November of 2008. Along the way, he earned 2 NASA Group Achievement Awards, one for NASA SETI project and one for Advanced Spaceborne Thermal Emission and Reflection Radiometer Aster, and a NASA JPL Center Award for his role in establishing a Center for Long Wavelength Astrophysics at JPL. His research in the Radio Astronomy Group focused on the outer planet atmospheres and magnetic fields. He was an atmospheric radiative transfer specialist for the Advanced Spaceborne Thermal Emission and Reflective Radiometer and a geological remote sensing instrument that launched on the Terra satellite in 1999. He was an image processing specialist for the Infrared Spitzer Space Telescope as a member of the Center for Long Wavelength Astrophysics at JPL. Tim also is an amateur astronomer and has been an astronomer at the Garvey Ranch Observatory in the city of Monterey Park since 1975, with an extensive experience in public outreach. He has been elected president of the Los Angeles Astronomical Society 12 times and received the Society's Lifetime Achievement Award in 2004 and is recipient of the 2015 G. Bruce Blair Medal for the Consortium of Western Amateur Astronomers. Tim has been a volunteer at Mount Wilson Observatory since 1981 and is one of the founders of of both the docent and session director programs. He's elected to the Board of Trustees of Mount Wilson Institute in September 2015. Tim is also a veteran of the U.S. Air Force. He graduated from the Defense Language Institute at the Presidio of Monterey in '72, passing the exit exam in both Russian and French. He spent the remainder of his tour of duty on the technical staff of the U.S. Air Force School of Applied Cryptological Sciences at Goodfellow Air Force Base in San Angelo, Texas. While not involved in astronomy, Tim was also an active tournament chess player. At his youthful best, he was ranked in the top half of the expert class, one step below National Master, and has earned a few chess club championships and tournament prizes. I was given Tim's contact information by Katie Steinecke, the former director of the Vatican Observatory Foundation, who I believe is also on the board of Mount Wilson. And she said, hey, you might want to have him talk. So, Tim, take it away.
Boy, well, after an introduction like that, who needs to hear a talk? Well, you're going to hear one anyway. I turned on my camera for the introduction, and so you could see my Dumbledore smiling face. But when we were doing our tests earlier, it's evident that if I turn off my video, it will not stress my limited bandwidth as much, especially because my slides have a tendency to be a little late in transferring. So my talk might be a little bit longer than expected, but I am the lead instructor for all the volunteers, staff, session directors, docents for the science and history of the observatory. And the last time I did that, I spent 4 hours at the microphone in a day-long session, and it'll be a bit longer next time. So consider yourselves lucky that you're not doing that today instead. So I'm going to first share my PowerPoint. Which you can all hopefully now see or will momentarily. And then I'm going to see if I can, well, okay. There's no easy way here for me to turn off my video. So we'll see how that, without turning off my slide. So we'll see how this works. You get to look at me while I talk, and we'll see if this proceeds. Well, what I want to talk about is Mount Wilson Observatory, and this is really the place where modern astrophysics was born. What's unique about it is that the science that we call astrophysics was done basically in secret by people who were supposed to be doing something else most of the time. A few people here and there. Mount Wilson Observatory was the first institution dedicated to the study of astrophysics. And these two guys you should see here, Andrew Carnegie and George Ellery Hale, are the money and the brains behind Mount Wilson, because everything like this takes money and brains. Carnegie was the richest man in the world, one of the richest men in world history, worth what would be well over $100 billion in today's money. And George Ellery Hale was a nearly insanely driven physicist out to accomplish all kinds of great things. So with their combination of money and brains, we have not only the first institution dedicated to astrophysics, but the observatory and George Hale and James Keeler coming together to found the Astrophysical Journal created a community of astrophysicists so they could talk to each other through their various papers and actually have meetings. And Hale did a whole lot of other things I probably won't have time to talk about anyway. And what I want to start off doing is, since Hale is the driving brain behind the observatory, I want to talk about him a little bit and where he came from and kind of how he got to be the person that he was. And I want to describe the milieu into which he was born. His father was wealthy and made a lot of money in the elevator business after the Great Chicago Fire, when Chicago went from being a one-story town to a skyscraper town. George was born in 1868, and he got his degree in physics from MIT in 1890. Physics as a science, the way we think of it now, shows up in the 1800s. Thermodynamics, in 1850, it was Clausius started the classical thermodynamics, really got on the board when he formalized this concept of entropy in the second law of thermodynamics. It was in 1877 that Ludwig Boltzmann put that together with statistical mechanics and and the statistical definition of entropy. Spectroscopy was particularly important. Fraunhofer and then Kirchhoff and Bunsen in a chemistry lab were able to prove in the 1850s that a number, all the elements, they produced unique spectral lines. So you could see what elements were there just by looking at the spectral lines. The theory of electricity and magnetism was born. And in 1868, George was born. In 1870, when George was 2 years old, Homer Lane, an American physicist, published the first paper, to the best of my knowledge, a real physical analysis of what the interior of the sun should look like. It was real physics for the first time. People weren't just guessing. So Hale was born into a time when physics was a really exciting science and things were moving fast and everybody wanted to get on the gravy train of physics, and George was one of them and very driven to accomplish something. So his rich father built his own observatory for him in 1891 that's pictured here, and he got his 12-inch Clark refractor in 1892. Now I have to forward there we go. George invented a device called the Spectra Heliograph. And if you can see my cursor, we're showing a little arrow, which I hope you can. So this device here is the business end of it, or here on the picture on the right. It's a device that allows you to image the sun in particular in one spectral line. And I'll show the effect of that in a few minutes. George, throughout his life, was fascinated by the problem of stellar evolution, and in particular, the study of the sun. And he devoted his life to the study of the physics of the sun, as well as allowing others to study the physics of stars. Now, when he came to Pasadena and came to found Mount Wilson Observatory, he was already famous and well known. He's well known for his work at his own observatory, which made him locally famous, got him an appointment on the faculty of the University of Chicago. There he convinced streetcar magnate Charles Yerkes to pay for Yerkes Observatory, because Yerkes, who had already been in jail a couple of times, probably for fraud, and was kind of a sleazebag gangster mafia guy, was convinced by Hale and the Chicago president that if he paid for the biggest telescope in the world, people would like him better. Whether they ever liked him better or not, I don't know, but it worked. He paid for the largest telescope in the world. The telescope is seen here up on the top, the 1 meter, 40-inch refractor. And of course, the observatory building is down on the bottom. One of the things unique about Mount Wilson is that the telescopes are not all tethered to a single building like this. They're in individual domes, the way they are now in all observatories. But Mount Wilson was one of the early observatories to do that. There was a plan between Harvard College Observatory and University of Southern California to build an observatory on Mount Wilson. And this was done while Hale was actually working at Harvard College Observatory.
Sorry, Tim.
1889 to 18. Yeah. Somebody's interrupting.
It doesn't look like the slides are advancing.
They're not, huh? They're advancing for me. Well, I don't know what to do about that.
Nope. Now they are advancing.
Aha. So I'm going to temporarily see if I can kill my video. If I can get back. I'm going to have to, now here we go. I'm going to stop sharing for a moment. I'm going
For a
to,
second, they were working.
They were, okay, now I'm going to stop my video again. Let's try this again and see what happens.
All right, we see it coming up.
Okay, now you should see a video with the telescope and a snow-covered observatory dome, a slide.
Yeah, we see the entire screen with that slide on it.
Okay, now if I go back one, you should see Hale with Yerkes Observatory.
All right, we're not seeing that.
This is probably the problem we had setting up.
Okay, now we are seeing it.
Or that seemed to be cured by my turning off my video, which I've done. So now I'm going to go back to the snow-covered observatory. How long does it take to go forward?
Appears to be stuck at the observatory.
Well,
Give it more time.
I don't know what to do about
There
that.
you go. It worked.
Yep.
Okay, so it appears that my slides are advancing extremely slowly.
Just got to be patient, I guess.
Yeah. I'm me.
Well, I think we just continue with your talk. We were listening to your words, and in the slides, hopefully we'll catch up.
Okay, well, so Mount Wilson Observatory was founded as Mount Wilson Solar Observatory in 1904. And if you ever see the slide that I have up now, which is an aerial view of the observatory, you'll see two conspicuous towers up in front. The tall one on the left is the 150-foot solar tower telescope, and over to the right of it is the 60-foot solar tower telescope. And just under the 60-foot tower is a horizontal building, the Snow Solar Telescope, which was the first solar telescope to come up the mountain in 1904. The domes for the 100 inches, the big one on the left, and the 60 inches, and basically in the center of the image. I'm going to talk about all of them at some point. But remember that Hale was particularly interested in studying the sun, and so it's not surprising that when he established the observatory, it was a solar observatory. And this slide shows what the telescopes looked like back in 1910, roughly. The horizontal telescope has celestat mirrors that are hidden behind the little building on the left. The 60-foot tower didn't have its dome yet, and the 150-foot tower behind it. What's really important about these telescopes, they were the largest and most capable solar telescopes in the world from 1904 until 1962. So throughout the entire first half of the 20th century, solar astronomy was dominated by Mount Wilson Observatory. Now, in 1904, I have to remind you there were no cars, and someday with luck, you'll see a slide with a bunch of mules on it. And that's how stuff got up the front of the mountains back in the old days. And one famous astronomer, Milton Hummerson, who some of you may have heard of, who worked with Edwin Hubble, and we'll talk about them later on, discovering the universe, basically started out pushing mules up the mountain and became interested in the daughter of the chief technician of the observatory and came looking for a job. They handed him a broom, and he started out as the janitor and worked his way up to a world famous astronomer. You can't do that anymore today, but back in the early 20th century, you could. So the science that came out of Mount Wilson Solar Observatory is really significant in that at the dawn of the 20th century, nobody actually knew what the sun was, other than that it was big and hot. And Homer Lane had made his attempt in 1870 to describe what the physics of the sun must look like. And there were a few more stumbling efforts to do that in the late 1800s. But basically, nobody knew what it was, and they had its chemical constituents all wrong. So one of the big mistakes they made was the assumption that the sun is made out of exactly the same stuff as the Earth in exactly the same proportion, which means mostly heavy elements, iron, rock, carbon. And so someday you'll see a slide with a sunspot on it and a reference to a paper by W.E. Wilson, no relation to Mount Wilson, in which he opines that the bright layer of the sun, the photosphere, is actually solid carbon grains. And the reason that sunspots are dark is that they're much hotter than the surface around them. The solid grains have been pounded into a gas, and the gas is optically thin compared to the solid grains, and so it will look darker because it will radiate much less efficiently, even though it's hotter. Now, in modern terms, that's just completely ridiculous, but back in those days, nobody knew any better. So in 1906 to 1907, using spectroscopy, laboratory calibrated spectroscopy, because we're doing astrophysics, George Hale, Walter Adams, and Henry Gale proved that the reason sunspots are relatively dark compared to the rest of the sun is that they're colder. And this was the first really objective demonstration of that, and a really early success of astrophysics, where you take laboratory calibrated physics and use it to explain an astronomical observation. Another major success was the very first hydrogen alpha images ever made. So George studied the sun at his Kenwood Observatory at home and at Yerkes in blue light, the calcium H and K lines, and hydrogen delta, gamma, beta, all of which were violet and blue. There were no photographic emulsions on the glass plates that were sensitive enough to the red, deep red color of hydrogen alpha to make it doable. But eventually, Ferdinand Ellerman, working at Mount Wilson Observatory along with the chemists who developed the photographic emulsions, came up with a good one for the deep red. And Hale used his Spectra Heliograph, which I described before, to image the sun in pure hydrogen alpha light. The two images that you will see, one on the left, 28 March 1908, is fuzzy because there were clouds, overcast weather that day, but the one on the right looks much better. And you can see features that you would recognize, like the dark feature on the top is a hanging prominence above the surface, seen from above, not on the edge of the sun. Well, Hale looked at this and immediately thought, oh, there are shapes and forms in this image that make me think of magnetic fields. I'll bet there are magnetic fields on the sun. And so he went looking for them. And very shortly thereafter, in June of 1908, he found them using the 30-foot spectrograph on the 60-foot tower telescope. He found magnetic fields in sunspots and demonstrated the bipolar nature of sunspots, that they're two and opposite magnetic fields. I'll talk about that again in just a minute. But this is important because these are the first magnetic fields ever discovered off the Earth, extraterrestrial magnetic fields. And this is the beginning of the modern adventure of observationally determining the real physics of the sun, which had to be either guessed at or tried theoretically before, like Homer Lane had done. But now Hale is really going to work on observationally understanding the sun using Zeeman splitting in spectroscopy to identify the magnetic fields. And there's a list of papers here that show mapping the general magnetic field of the sun as well as the magnetic field in sunspots. And he was able to notice that the sunspots change their magnetic polarity from one sunspot cycle to the next. And you will see a diagram, figure 18, from his 1925 paper on the law of sunspot polarity. Along the horizontal axis is the date in years and solar latitude, north and south. On the vertical axis, and the sweeping curves you see show the track of sunspots as they form. At the beginning of a solar cycle, sunspots tend to form higher up in latitude, around the 30 to 40 degree line. And as the sunspot cycle progresses, sunspots tend to form at a lower latitude until the sunspot cycle comes to an end when they're close to the equator. In the first sunspot cycle they looked at in 1908, the leading spot had a south polarity in the north geographic hemisphere, and in the southern hemisphere, the leading spot had a north magnetic polarity. But in the next cycle, that pattern reversed, so that in the northern geographic hemisphere, the magnetic field of the first sunspot was a north-facing field and south-facing in the southern hemisphere. So he realized that the sunspot, roughly 11 and a half year cycle, as he put it, is half of a 23-year magnetic cycle. I don't think he fully understood what we do now, that the magnetic field of the sun actually reverses itself, but they knew there was a magnetic cycle, and sunspot counts had already demonstrated earlier that there was some kind of a double cycle going on, roughly 23 years. Also, using the 60-foot and the 150-foot tower telescopes, two major discoveries. One was that in the 1950s, Babcock's Harold and Horace, a father-son team, built the first really effective photomultipliers able to measure magnetic fields and actually map the magnetic field of the sun efficiently. And so they were able to prove conclusively what Hale thought he had proven as early as 1913, but was really noisy and unclear. The sun really did have a significant global magnetic field, and you'll see a magnetic map of the sun. But more importantly, they also made Dopplergrams of the solar surface, looking at material that's coming towards us in Doppler shifted blue, going away from us in Doppler shifted red. And by studying that, not only do you get convection patterns which dominate the image, hot gas rising and coming towards us, then cooling and then sinking back, but there is another set of vibrations imposed on top of that, initially discovered as 5-minute period oscillations, which are basically standing waves acoustic waves, really, where the sun is a spherical cavity resonator. This is the basis of what is now called the science of helioseismology. And applying that to other stars is now called asteroseismology. It's important in cutting-edge stellar physics today because it allows you to diagnose the real-time interior structure of the sun or the star in a way that electromagnetic waves and light simply cannot do, because these are acoustic waves that travel right through the sun and are not distorted by its internal plasma. So you can diagnose the interior of the sun the same way Earth seismologists diagnose the interior of the Earth, and that's why it's called helioseismology and asteroseismology. And this, to this moment, is really basically the cutting edge of solar astronomy and solar physics and stellar physics as well. So this slide will summarize the solar discoveries made at Mount Wilson Observatory, and the background is a modern hydrogen alpha image made just last month by Alan Friedman, whose website is avertedimagination.com. And if you really like H-alpha images of the sun, you should check Alan Friedman's website, because he's quite the amazing solar photographer. Discovering the true reason for sunspots being dark because they're cool. Several of the discoveries relating to magnetic fields, sunspot magnetic fields, the sunspot magnetic cycle, the overall magnetic field of the sun. Today, we know that magnetic fields are ubiquitous and very important in stellar structure, stellar physics, stellar evolution, and really in all aspects of astrophysics. Galaxies, extragalactic astronomy, magnetic fields are everywhere. And so it's a common joke amongst astrophysicists that if you see something you don't understand, it's just a magnetic field, don't worry about it. And of course, the sciences of helioseismology and asteroseismology. And assuming the image eventually becomes visible, here is Alan Friedman's image not dimmed, so you can read the foreground. And you'll notice that he caught the International Space Station transiting in front of the sun. And you can see the features that George Hale could actually see, the large arcades up above the chromosphere. Those actually showed up on George Hale's first hydrogen alpha images of the sun. So while Mount Wilson Observatory is famous for Edwin Hubble and its cosmology, it's really important to remember that our understanding of the sun and solar physics, sunspot magnetic fields, there's a lot of work done on solar flares that I haven't had time to go into here. And since there is a connection between solar flares and the Earth, especially now with power grids and satellites, GPS satellites, this really is still practically important science and not just astrophysically important if you want to understand the sun. Now, I want to talk about the 60-inch telescope. Hale knew very well that to really understand the sun, you needed to understand how it compares to other stars, which means you have to study other stars, because he really was interested in stellar evolution, not just the physics of the sun. So the 60-inch telescope, the dome of which is in the middle of the aerial image of the observatory, first came up the mountain in 1908. And this image, which hopefully will catch up with me eventually, is cutting-edge 1908 automotive technology, custom made by the Mack Truck Company to get a big, heavy steel optical tube assembly, probably weighing about close to 20 tons, up the mountain. There are two steering wheels. This is 1908 power steering. The wheels are connected by a steel shaft so that they're rigid, and a drive chain like a motorcycle chain. So power steering in 1908 is two guys instead of one. It has a gasoline engine that powers an electric generator that powers an electric motor for each of the 4 wheels. Each wheel can turn forward or backwards independently, and the road that the telescope went up was so sharp and so windy that you needed to spin the vehicle on its central axis to get it around some of the hairpin turns. So you would turn the wheels forward on one side, backwards on the other side, and by adjusting the speeds, you could twist the truck left or right. And here's an image of it on the road that went up from Pasadena. The modern highway was built in 1935. So all the old stuff came up a widened and specially constructed road from Eaton Canyon, Altadena. It is 1908, so even though we have a cutting-edge, brand-new designed truck, it still needs a few mules to help it get up the road, because they just didn't build them then like we build them today. The rear axle is independently steerable as well, and you can see the rear wheel driver obscured behind the telescope tube, and then, of course, the mule driver up front. So the 60-inch telescope is a really major innovation in the technology of doing astronomy, just as the solar telescopes were. You do have to remember that technology and science really go together. The need to do new science will drive new technologies or extensions of old technologies, and sudden advances in technology will present scientists with the ability to do things they'd never done before. So people had built big telescopes in the past, and an English amateur astronomer named Andrew Common built his own 60-inch telescope back in the 1860s, probably in the late 1800s, but it wasn't very good. He could never get the mirror surface properly figured. And primarily it's because they just weren't patient enough. George Ritchie of Ritchie Chrétien Optics fame designed the 60-inch and did figure the mirror. He made sure that it was on a mount hefty enough to hold it. His major breakthrough in crafting the mirror was incredible patience. He took years to do what other people wanted to do in a few months, very carefully polishing the surface of the mirror. The pictures of the 60-inch show it as it is now with an eyepiece holder, because we have people actually look through it, although it wasn't designed for that. And in 1910 picture, there's a low resolution spectrograph connected to the Cassegrain focus. So this telescope has several innovative features, one of which is that it actually floats in mercury. In the 1910 picture, you can see that the mercury tub is open, and you can see the flat cylindrical float that holds up the telescope, so the mechanical bearing only has to carry about 10% of its weight. It's sealed up these days. The front end of the telescope can be removed to change the secondary mirror. Nobody had ever done that before. When Andrew Common made his 60-inch telescope, he built it as a Cassegrain, built it as a Newtonian, climbed all the way up to the Newtonian eyepiece at the far end of the telescope, almost fell off his ladder, panicked, came down, disassembled his telescope completely, and then rebuilt it from scratch as a Cassegrain so that he wouldn't have to go to the top of the ladder anymore. But nobody had ever thought to make the secondary mirror removable so you could change the optical configuration of the telescope. George Ritchie did that for the first time with the 60-inch, and so that nobody ever uses prime focus as far as I know, but it was used extensively at Newtonian, Cassegrain, and at the F30 Coudet focus. And the Coudet idea was a new one. And there were no large telescopes with Coudet light paths on them until George Ritchie made one for the 60-inch. and that allowed very high resolution spectroscopy, and spectroscopy is the key to doing astrophysics. So it's critical to have that ability. Now, want to compare the 60-inch to its competition. It's standard practice to refer to the 40-inch refractor at Yerkes as the largest telescope in the world at its time. It wasn't. The 48-inch Great Melbourne telescope was, 8 inches bigger. It had a speculum metal mirror, but was an inferior telescope for a whole bunch of reasons. It was not designed to photography. It was an f41 Cassegrain, so you had a pretty lousy eye relief. It's a tiny field of view designed to make hand sketches and drawings of Southern Hemisphere NGC objects. But it was built on a cheap mount. It shook when the wind blew, so even if you did try to take a picture with it, it wouldn't work. People didn't go there. Very few people used it. Nobody really cared much about it, and so it's just kind of forgotten in the history of astronomy, and everybody lavishes their praise on the 40-inch refractor, and most people don't even know the GMT of its day even existed. But there is a band of Australian enthusiasts at the moment trying to re-establish the reputation and rebuild the GMT, which was technically destroyed in the 2003 Mont Stromlo fire. But that telescope had, as far as I know, no original parts left anyway. So really wasn't the original GMT that was destroyed. A more realistic and more important comparison is with the 40-inch Yerkes refractor. So remember that the 60-inch was 3 telescopes in one, basically Newtonian, Cassegrain, and Coude, very important. But it's a reflector, and one of the problems with a refracting telescope is that if you want to do infrared astronomy, and in fact George Hale knew in 1896 that he wanted to do infrared astronomy, infrared won't get through the glass on a refractor lens, so you have to have an open tube and a reflector. And in any case, chromatic aberration means that with the 40-inch refractor at Yerkes, to do spectroscopy, you had to photograph each individual spectral line one at a time, moving the camera to where that wavelength came to focus, and that unbalanced the telescope, which means you need to rebalance the telescope. It's tedious and arduous, and nobody really wanted to do it. With a reflector like the 60-inch, all the wavelengths come to focus at once, and you can photograph an entire spectrum at once. Also, the 60-inch is much smaller and in a much smaller building, so it's a lot cheaper. So there were a lot of reasons for going to a reflecting telescope and getting away from the refractors. And indeed, the 40-inch remains to this day the largest practical refracting telescope ever made. And the 60-inch is the great grand ancestor of every major astronomical telescope existing in the world today. They are all based on the premise originally established by the 60-inch telescope. And its claim to scientific fame is primarily that Harlow Shapley used the telescope during the period 1914 to 1918 to discover the Milky Way galaxy, which sounds a little pretentious because it's a conspicuously naked eye object in any dark sky, and you've probably all seen it more than once. But the point is, for thousands and thousands and thousands of years, people looked at the Milky Way and did not know what they were looking at. They just a bright line of stars in the sky. It was not until Shapley observed Cepheid class variable stars in globular clusters, was able to determine their distances, observed some O class and other stars, and was able to map out the Milky Way galaxy and basically create a schematic for what it looked like, that it was a disk, that it kind of looked like the spiral nebula, but it wasn't really a spiral nebula in his mind anyway. He thought of it as almost an Oreo cookie with 2 parallel layers and a dark zone of avoidance in between, as he called it. We now know that's dust clouds, but he didn't. but still it's the first schematic layout of the size and shape of the Milky Way galaxy. And here you see a plot from one of his papers in 1919 where he lays out the positions of globular clusters that form a roughly spherical halo around the Milky Way. But as you can see from the circles I've drawn, you are here is where we are and where Shapley was and where the solar system is, and the center of the distribution is over there. This is, believe it or not, the very first real observational evidence that the sun, solar system, the Earth, us, we are not at the center of the universe. As Shapley mapped out the Milky Way galaxy, it was commonly assumed that he was, in fact, mapping out the entire universe. So when Shapley got done in 1919, 1920, the common assumption was that the entire universe was what we would now call the Milky Way galaxy. And while philosophers have argued for ages and ages about us being at the center of the universe, it wasn't until 1914 to 1919 that Harlow Shapley proved rather conclusively that we are not. This is what we think the Milky Way looks like today. I made an effort to find a galaxy that looks as close to being like the Milky Way as I could, UGC 12158. Our Milky Way is probably about 200,000 light years across. Shapley thought it was 300,000, which is a little too big. The standard answer you get from everybody these days is 100,000, which is definitely too small. So 200,000 is probably the right number. It rotates differentially, so the sun takes about 250 million years to make one rotation around the Milky Way. But the spiral arms only take about 50 million. They move much faster because they are waves of star formation, not structures of stars. And those waves are moving much faster than the stars are. Another invention of the 60-inch telescope I made by Walter Adams was something called spectroscopic parallax, which has nothing to do with parallax, but they knew that trigonometric parallax gave you a distance, and this was a spectroscopic method of getting a distance, so Walter Adams called it parallax, so people would understand that it was a distance. Basically, you use the Hertzsprung-Russell diagram, which is shown here on the left. You pick off the spectral type and go down spectral class, and color are plotted horizontally. So if you find one and draw a vertical line, and then you look for what's called a luminosity class, which you can get from the width of the spectral lines, and swing on over to the right, and you'll see a couple of white lines on the diagram, the HR diagram, that show you can pick up an absolute magnitude. That's how bright is it really. The difference between that and the apparent magnitude gives you a distance in parsecs if you write the formula correctly. At the dawn of the 20th century, people knew the distance to roughly 60, as in 60 stars, due to trigonometric parallax, and nothing beyond that. So nobody knew the distance to anything. Everything was a guess. This method and more rigorous trigonometric parallax, but mostly this method, allowed Mount Wilson and other observatories to quickly establish distance to hundreds of thousands of stars. It was an amazing growth during the early 20th century of how we understood the distances to other stars. Another project, the 60-inch, was used on, it's called the HK project, studying the H and K lines of calcium. It may seem a bit paradoxical, but when there are lots of star spots or sunspots, the stars or the sun are much brighter in calcium light than they are when there are no sunspots, and that's because of the plage area, as they call it, around the spot. So by monitoring the brightness of stars specifically in calcium light, you can see the star spot cycle, and there are several plotted here which show the sun top center and other stars, some of which have cycles that look like the sun, some of which are longer, some of which are shorter, one that doesn't seem to have much of a cycle at all. So it shows that the sunspot cycle is not unique to the sun. There are star spot cycles around most other stars, but the periodicity varies from stars to stars. It could be random, it could be more periodic like the sun. But this is another way to assess the importance of magnetic fields in stellar structure. And it's how you learn about other stars. Now, as soon as the 60-inch telescope was built, see, Hale had a habit of pressing every technology that he ever encountered to the breaking point. The 60-inch telescope mirror was ground and polished at the Saint-Gobain Glassworks in France, and it's a really nice, clean piece of glass, so he immediately wanted a bigger one, the 100-inch mirror. There were 8 attempts at the same glass-making company to make a 100-inch mirror. The third attempt succeeded, the other 7 all failed during annealing. He had successfully pushed glass-making technology to its limits, and both the 100-inch and 60-inch mirrors were the largest single pieces of glass ever made for any purpose at all in their day. So the 100-inch telescope had to be brought up the front of the mountain just like the 60-inch, but the optical tube assembly for the 100-inch is much too large. So here is a new 1917 truck, even better than the 1908 truck. This one never needed mules to help it pull it up, and it didn't need power steering, two-wheel power steering anyway. And here is a picture of the bottom section of the 100-inch tube outside the offices of the Carnegie Observatories on Santa Barbara Street in Pasadena. And here are a couple of pictures of it going up the mountain. And it was a dirt road. It was widened and reinforced, but that doesn't mean that everything always went nice and smooth. Fortunately, the truck and the telescope section did not roll all the way back down to Pasadena. And you can see in the lower photograph, it's been tied off to several bushes and trees. And there are a bunch of people standing around trying to figure out what to do about it. And they're up in the mountains, and you'll notice these people, one guy wearing his coat, and there are a number of people wearing ties, and they dressed for the occasion, even though they're working in the dust and dirt. And here is the 100-inch under construction. The main drive gear of the 100-inch telescope is 200 inches in diameter, 5 meters, the same size as the primary mirror in the Hale telescope at Palomar. Too big to come up the mountain in one piece, and you can't cut the teeth down at the bottom, bring the two halves up separately, and put them together at the observatory, because there will always be a glitch in the drive system of the telescope where the two halves of the wheel come together. So they were brought up separately, riveted together at the observatory, and once everything was all together in one piece, instrument maker Clement Giacomini ground the teeth into the drive gear in place, and you can see him in the lower left doing that. It's unique. So that mirror came up the mountain in July 1st, actually, of 1917. In April of 1917, the United States entered World War I. And by July, there were American troops in Europe. But a war fever had come to the country. And it was a great patriotic display to get the 100-inch mirror up the mountain. And so there are American flags hanging around all over the place and women dressed as Lady Liberty and a whole bunch of other stuff. The truck did not need a mule to help it get up the hill, but it did need to stop and pour water in the radiator. It is 1917 after all. And here it is. The mirror is in the truck in the rear under the canvas coating where its wooden case is, waiting for a water change. Here is a picture of the mirror seen from the top and seen from the side. Remember that only 1 out of 8 attempts survived. And it was rejected when it arrived at the observatory because the glassworks did not have a ladle big enough to pour that much glass at once. So they poured a layer, filled up, poured another layer, filled up, poured another layer, 3 layers of glass and 2 interfaces, because as you're busy getting more hot glass, a little bit of cooling goes on. And there is now 2 layers of bubbles trapped between the 3 layers of glass. Trapped in discontinuities in the glass, these bubbles could not outgas during annealing as would normally be the case. So on the edge-on view, you can see that the glass is full of bubbles. And while it's annealing, it's hot. There are convection currents in the molten glass. So the bubbles are not nice and evenly distributed in flat planes. They've been carried around inside the glass by convection. So when it arrived, George Ritchie, who had done the 60-inch telescope, rejected it, partly because he was afraid that when he ground and polished the mirror, he would expose the bubbles, in which case it would be completely useless. And another worry they had, which we now know is not something to worry about, was that thermal expansion and contraction would cause the glass to separate into 3 layers along the discontinuities that you can see. But it was the only one that survived, and eventually they were forced to just use it and make a telescope out of it. And George Ritchie complained vigorously that it was a terrible waste of his time. And he wanted the 100-inch telescope to be a Ritchie-Chrétien system, and George Hale didn't want him to do that. And so Ritchie went to John Hooker, who was paying $45,000 for the mirror, told him, tell Hale to do it my way. That's insubordination in anybody's book. And eventually the relationship between Hale and Ritchie became strained enough that Ritchie had to be asked to seek employment elsewhere. But he did finish the mirror, and both the 60-inch and 100-inch mirrors are diffraction limited. And here is what the 100-inch telescope looked like in 1917. And it looks pretty much the same now, except, of course, that these days it's in color, and in 1917 it was in black and white. Like the 60-inch, it floats in mercury, but it's on a dual point English yoke mount instead of a single point fork mount. The moving weight of this telescope is 100 tons, and they were a little nervous about just putting one shaft, and so they bear the weight at both the top and bottom. Here is an image of the logbook for the first night of observing. I wrote this in 2017. That's why it says it's 100 years. It's now, of course, 105 years. It lists all the people who were there and the objects they looked at. We now know that they did not look at the objects noted here in the order they are noted because it was impossible to do that. So exactly what was actually the first object to be looked at is a matter of spirited discussion amongst astronomical historians, whether it was Jupiter or Saturn or a star. But it also lists the names of everyone who was there, and they were all staff especially the ordinary staff, not famous people who worked on it, like the electrician and the machinist and the carpenter, all here to do first light. When they looked through the telescope, it was a horrifying image of multiple, whatever it was they looked at was there in multiple images. And then somebody realized, oh, the sun had been shining on the mirror during the day, careless. So they closed everything up and let the mirror cool off and tried to sleep. Nobody did. Came back a few hours later in the wee hours of the morning, and it was great. It was indeed. The problem was just the sun shining on the mirror. The only outside guest was an English poet named Alfred Noyes. George Hale was what we might call a Renaissance man or a man of letters. He was a physicist devoted to solar and stellar physics, but he was also well read in literature and poetry. He was interested in Egyptian history. And Noyes had been working on a what became a 3-volume poetic history of science called The Torchbearers, but he hadn't started writing yet because he didn't quite have the motivation to do it. So Hale invited him because he wanted an artist or a poet to be there to understand what was happening at the moment of first light. And Noyes later said this was the inspiration he needed. And he went to work on The Watchers of the Sky, which was the first volume of his trilogy, The Torchbearers, on the poetic history of science. And remember, this is when the United States has gone into World War I. And so military metaphors abound. And this is what Noyes wrote in Watchers of the Sky about his experience for first light on the 100-inch. He wrote, "High in heaven it shone, alive with all the thoughts and hopes and dreams of man's adventurous mind. Up there I knew the explorers of the sky, the pioneers of science, now made ready to attack that darkness once again and win new worlds. Tomorrow night they hoped to crown the toil of 20 years and turn upon the sky the noblest weapon ever made by man." Now, I've always liked the idea of the 100-inch telescope being the noblest weapon ever made by man. And I had no idea you were going to have somebody read poetry at the beginning of your meeting. And so now you get it in a double dose. Congratulations. So why is the 100-inch telescope famous? Primarily because of Edwin Hubble. At the time, say around 1920, nobody knew what the spiral nebula things that we now call spiral galaxies were. And there was a spirited debate over whether they were things very far away or things nearby. And there was good evidence at the time to choose either one. For the faraway crowd, there was a tendency for nova to go off, or so it seemed, in the spiral arms of the spiral nebula. And nova were very dim, but we know they're intrinsically very bright. So in order to look dim, they must be very far away. But an astronomer named Adrian von Manen was convinced that he could see the proper motion of the rotation of the spiral nebulas, in which case they must be very nearby. Nobody has a clue to this day what it was that convinced Adrian von Manen that this was the case, but we now know that he was completely wrong. Hubble wrote his doctoral thesis at the University of Chicago, and Alan Sandage, one of the famous Carnegie astronomers, called it the worst PhD thesis he'd ever seen in his life. But that's because Hubble was very anxious to get into World War I, and he slapped off a fast thesis, handed it in. It didn't really matter because Hale had already told him, when you get back from Europe, I have a job waiting for you. So he went to Europe. He rose to the rank of major in the U.S. Army, and I think he worked in the ambulance corps. In any case, my memory is that he was never anywhere near combat. And when World War II came along, he worked on torpedo propulsion systems and was actually a lieutenant colonel at one point, probably in the Army Reserve.
So Tim, we're coming up on an hour. I hate to say this, but we have to close up pretty soon.
We do.
The audience at Cranbrook has to get out and they have to pack up.
Yeah, I tell you what I'll do. I will simply stop, and you can ask questions, because I think it's important for people to be able to ask as many questions as they can. I always talk too much anyway. It's a habit of mine. Sorry about
Diane,
that.
do we have a few seconds for a cup question?
David Levy has one.
Yeah.
Yeah, I don't hear me. I don't think you're gonna hear me. I'm sorry.
Yeah, you can hear David. Go ahead.
You can?
I can hear you.
I can too.
Yes, go ahead, ask.
Of all the people who are here, wonderful lecture, absolutely wonderful lecture. There are two you may not have known about. One of them is the Webb telescope, listening from the L2 position as President Biden just released its very first image. We're going to get a lot more tomorrow.
Yeah.
And the Webb telescope wants to congratulate you on your fabulous lecture today. The second person, in quotes, who is here for your lecture you may not know about was the sun itself. And with all of the activity going on in the sun now, the sun had a chance for an hour to think about the wonders of what people in the past, on a world only 8 light minutes away, were able to learn and understand about it so long ago. Thank you so much for this lecture. I really loved it. Thank you.
Well, I appreciate that. I'm sorry I went too slow and too long, but there's just too much to say about Mount Wilson. You know? That's my excuse. I'm sticking to it.
Sad part is he didn't live to see the 200-inch. He wanted to, but the war killed that, right?
Yeah. The war delayed the 200-inch significantly.
Yeah.
Do we have, come on up, Mike.
Microphone, can you hear me?
Somebody can hear him.
Here.
What is that galaxy that the number of the galaxy that is similar to our own?
Oh, the galaxy, you want to know which galaxy was that?
Yeah.
That galaxy is cataloged as UGC 12158.
Isn't our galaxy a barred galaxy though? It's not quite that. Isn't that true, or am I?
Oh yes, our galaxy is a barred spiral galaxy.
Okay.
And in fact, you could say it has 2 bars. It looks pretty. And I was going to ask, because I noticed your name. There's a docent, longtime docent at Palomar Observatory named Michael Burton, who spells it exactly the same as you. Are you related to Michael at Palomar?
No, I am not.
Oh,
well. But I know who he is. How's that? So
okay.
I linked that galaxy mentioned in chat. It is pretty cool looking.
Okay, thank you.
Go ahead and ask your question from where you are.
All right. One of the things I was reading about when I was learning about the Hubble constant was that actually early on in the late 20s, a person.
There's a great deal of feedback and echo, and it's hard for me to hear the question.
Yeah, Adrian, we got 2 mics picking up in there.
I have a question.
Yeah, Catholic priest by the name of,
Question, Tim?
Yeah.
Are you aware of the connection between Mount Wilson and the McMath Observatory?
Let's see, I know there was a guy named Livingston, I think, who went to work, was stolen away from Mount Wilson to work at McMath Pierce. In fact, just yesterday I was at the observatory all day with Claude Plymate, who worked at the Big Bear Solar Observatory for so long, is now retired. He worked there with Kid Peak at McMath Pierce.
Hello?
Okay, now I can hear there's
Tim.
Echoes and feedbacks and things.
Tim, this was the McMath Holbert Observatory, which is about 20 miles from here.
Okay, no,
And
I'm not aware of a connection, but I'd like to know it if there is one.
There was a connection back in the early 30s.
Do you know what it was? Who?
Russell Porter was here at Lake Angeles. Hale was helping McMath construct the solar observatory here in Lake Angeles, Michigan, which operated for about 50 years.
Okay. Yeah, I know Russell. I know who Russell Porter is. I never met him, but I'm not that old. But I'm working on it, but not quite yet.
Okay, well, it's 9:40 and Cranbrook has to vacate. So thanks everyone. Thank Tim for the presentation.
Okay.
Clap, clap, clap.
I'll try to be more efficient next time.
Great, it's fine. Tim, you did great.
Thank you very much. It was fascinating.
Thank you.
And good night, everyone. And for those at Cranbrook, you're probably going to be going over to Redcoat Tavern. I'm not going to be joining you because I'm not there. So have fun, everyone, and good night.
Night all.
Night all.
Night all. Thank you for listening.
All right, gang. Regarding the Redcoat Tavern, so for those of you who remember that we used to be able to chill there until midnight, now close at 10:30 and the closes at 10:15. So if you can get there by 10:15 and get your order in, have a good night. But I don't think we're having a party there tonight.
No, it's not.
Thank you.
Okay.
Thank you. Have a safe drive, everybody. Thank you very much, Tim. That was a fascinating talk and a